Have you ever wondered why an electron doesn't simply crash into the nucleus of an atom? It's a curious question, isn't it? It defies the logic we're used to in our everyday world. Here, objects don't just hang around without falling down. But in the quantum realm, things behave oddly. Electrons, for instance, seem to exist in a cloud-like state around the nucleus. They don't just plummet into it. Well, to understand this, we need to delve into the world of quantum mechanics. Quantum mechanics came into existence to explain the behaviors that classical physics could not. In the late 19th and early 20th centuries, scientists were grappling with phenomena that seemed to defy the well-established laws of classical physics. Light, for instance, behaved in ways that couldn't be explained by the wave theory of light alone. Enter Max Planck, a German physicist. In a bid to solve the blackbody radiation problem, he proposed a radical idea: that energy was quantized. This meant that energy could only take on certain discrete values, a concept that was a complete departure from the continuous nature of energy in classical physics. Around the same time, a young Albert Einstein was making waves of his own. He applied Planck's quantum theory to light, suggesting that light was made up of packets of energy called photons. This particle theory of light, along with Planck's work, laid the foundation for the new field of quantum mechanics. As the years progressed, more and more phenomena were found that could only be explained by this new branch of physics. Quantum mechanics provided the framework to understand the behavior of particles at the atomic and subatomic level, an area where classical physics was inadequate. Quantum mechanics was not just a new set of rules, it was a new way of looking at the universe, a new paradigm that challenged our understanding of the physical world. In essence, quantum mechanics was born out of the need to explain the inexplicable. The quantum world is vastly different from the one we perceive with our senses. Imagine a realm where the ordinary rules of physics are turned upside down, where particles can exist in two places at once, and where observing a particle can change its state. Welcome to the quantum realm. In the macroscopic world, objects obey the classical laws of physics. A ball thrown in the air follows a predictable path under the influence of gravity. But in the quantum realm, things are not so straightforward. Particles exhibit a strange duality, behaving as both particles and waves. This is known as wave-particle duality, a cornerstone of quantum mechanics. Take a photon, for instance. In some experiments, it behaves like a particle arriving at a single point. In others, it behaves like a wave, spreading out and interfering with itself. This isn't because the photon is sometimes a wave and sometimes a particle. Rather, it's always both. It's just that we can only observe one aspect at a time. Then there's the principle of superposition. In the macroscopic world, an object is either here or there. But in the quantum world, things aren't so black and white. A particle can exist in multiple states at the same time, thanks to superposition. A quantum particle doesn't commit to a definite state until it's measured. Until then, it exists in a superposition of possible states. It's like Schrödinger's famous thought experiment with the cat. The cat in a box is both alive and dead until someone opens the box to check. It's only at the moment of observation that the cat's state becomes definite. This is the mind-bending reality of the quantum realm. It challenges our intuition and defies our everyday experience. But it's not just abstract theory. Quantum mechanics underpins our understanding of the universe, from the tiniest particles to the vastness of space itself. In the quantum realm, things exist in multiple states at once until observed. Now, let's understand the basic rules that govern the quantum world. Quantum mechanics, the fundamental theory in physics, operates on a set of basic postulates. These postulates are essentially the rules of the game, the framework that defines how particles behave in the quantum realm. Our first stop is the wave function, symbolized by the Greek letter psi. The wave function is a mathematical description of the quantum state of a system. It's a complex number that provides us with crucial information about a particle. But here's the catch. We can't directly observe the wave function. Instead, we use it to compute probabilities. This takes us to our second postulate, the probabilistic nature of quantum mechanics. Unlike classical physics, quantum mechanics doesn't give us definitive outcomes. Instead, it gives us a set of possible outcomes, each with a certain probability. The square of the absolute value of the wave function, often referred to as the probability density, gives us the likelihood of finding a particle in a particular state. So instead of a definite position or velocity, we have a cloud of possibilities. It's a bit like predicting weather. We can't say for sure if it'll rain tomorrow, but we can estimate the probability. Next up is the principle of quantum superposition. This postulate states that any two or more quantum states can be added together, or superposed, and the result will be another valid quantum state. And conversely, every quantum state can be represented as a sum of two or more other distinct states. This is where things like Schrödinger's infamous cat come into play. The idea that a quantum system can exist in multiple states simultaneously, until we make a measurement. Speaking of measurements, this brings us to the postulate of quantum measurement. The act of measurement in quantum mechanics is a bit of an oddball. When we measure a quantum system, it collapses from being in a superposition of states to being in one definite state. This is known as the collapse of the wave function, and once we've measured a system, repeating the measurement will give the same result. However, the state that the system collapses into is chosen randomly, with a probability determined by the wave function. Finally, we have the postulate of time evolution. Quantum states evolve over time according to the Schrödinger equation. This equation predicts how a quantum system will change, giving us the future wave function based on its current state. It's the quantum equivalent of Newton's second law of motion. These postulates form the foundation of our understanding of the quantum world. The rules may seem strange, even bizarre, but they have been remarkably successful in explaining the behavior of particles at the smallest scales. And that, in essence, is the beauty and the mystery of quantum mechanics. Quantum mechanics is indeed a conundrum, but it's one that has revolutionized our understanding of the universe. Quantum mechanics has a reputation for being strange and counterintuitive. And while it may be, it's also been profoundly successful in explaining the natural world. That's because at its core, quantum mechanics deals with the world at its most fundamental level. It governs the behavior of particles, atoms, and even light itself. But the magic of quantum mechanics doesn't stop at the microscopic level. It has far-reaching implications even in fields that you wouldn't necessarily associate with physics. For instance, it's the cornerstone of modern technology. Without quantum mechanics, we wouldn't have semiconductors, and without semiconductors, we wouldn't have computers, smartphones, or the internet as we know it today. In the realm of chemistry, quantum mechanics is indispensable. It allows us to understand and predict how atoms bond together to form molecules. This has led to countless breakthroughs in material science, medicine, and environmental science. Even in the world of finance, quantum mechanics has found a place. Quantum computing, which leverages the principles of quantum mechanics, promises to revolutionize the way we solve complex problems, potentially transforming areas like cryptography and financial modeling. But perhaps the most intriguing aspect of quantum mechanics is its philosophical implications. It challenges our notions of reality, locality, and determinism. It forces us to confront the idea that the universe may not behave in ways that our human intuition finds comfortable or familiar. Despite its oddities, or perhaps because of them, quantum mechanics has been incredibly successful. It's been able to explain phenomena that classical physics simply couldn't. From the behavior of subatomic particles to the properties of black holes, quantum mechanics has provided answers where there were only questions. So, while quantum mechanics may seem strange, it provides a remarkably accurate description of the universe on the smallest scales. So, where does this leave us in our understanding of quantum mechanics? Let's take a moment to reflect. We've journeyed from the birth of quantum mechanics, navigating the twists and turns of this mind-boggling realm. We've grappled with its basic postulates and wrestled with the paradoxes that lie at its heart. Quantum mechanics, in its essence, is a theory of the micro-world. A world where particles can be in many places at once, where they can tunnel through barriers, and where they can be entangled, affecting each other instantly no matter the distance. It's a world that defies our everyday logic, yet it underpins the fabric of our universe. The influence of quantum mechanics stretches far and wide, from the technology in our hands to the stars in the sky. It's a testament to the curiosity and tenacity of the human spirit, constantly pushing the boundaries of what we know and understand. Quantum mechanics, though baffling, is integral to our understanding